Welcome back. In this video, we're going to start talking about the wave equation. In the previous two videos, we talked about the heat equation. You've probably noticed I'm a bit behind. I'm actually recording this video on Monday, not the previous Friday, and we have homework due this week. But this lecture should be all you need to do to get you through the homework for the heat equation and the wave equation. The next lecture will add more detail, and we'll do some more complicated Fourier solution examples. And I'll also talk about something called traveling waves, which I'll introduce today. So we'll do more examples with Fourier series. Traveling wave solutions are called D'Alembert solutions. And I'll connect those two ideas together. Anyway, let's get started. So in this lecture, we'll talk about what the wave equation is and derive it for transverse oscillations. So you've heard of sound waves, of course, and you've seen probably waves traveling along a string. These are all examples of solutions to the wave equation. To motivate the subject, I'll introduce you right away to traveling waves. Just like for the heat equation, there are natural initial boundary value problems if you're trying to solve the wave equation on an interval. And you can solve those natural problems excuse me, by using building block product solutions that for the heat equation we got by separating variables, and the same procedure works here. And those building block solutions correspond to modes of vibration. You've maybe heard of, a lot of you have played musical instruments, and these are related to the vibrations that you get out of musical instruments, either string or woodwind. And the lecture will end with a Desmos example that we'll also do the computations for, and it illustrates everything you need to know to do more complicated examples with infinite Fourier series, in complete analogy to what happened with the heat equation. Okay, and then the second lecture, as I said, I'll talk about some using infinite superposition. I will expand on the idea of traveling wave solutions. You have some homework problems where you can work out the basics of this on your own. And we'll actually accidentally do one of those first homework problems in the warm-up exercise. And then we'll connect the Fourier series solutions to traveling waves and have one or two demos as well. Okay, so that's the plan. Here is the warm-up exercise to get you thinking about waves. So if you have a function u of x and t, where x is a spatial variable and t is standing for time, the partial differential equation, and it's a linear homogeneous partial differential equation that is used to describe the wave motion, is that the second partial of u with respect to t is a constant a squared, so it's a positive constant, times the second partial of u with respect to x. And if we choose a to be positive, that turns out it's to be the speed the waves are propagating. And to understand that right away, let's assume that this wave equation actually does describe wave motion, and let's try to make some easy solutions. So pick any twice differentiable function of a single variable, call it f of z, and then do the composition of that with as follows to get function of two variables. So let u of xt be f of x minus at, or f at x plus at, and let's check that those u's solve the wave equation. And so let's just start computing. So if u of xt, let's do it for the first case, is f of x minus at, let's compute the second t partial and see that it equals a squared times the second x partial. So the t partial, by the chain rule, I have to take the derivative of the outside function, which is f, so I get f prime at whatever's inside. Then I have to multiply by the derivative of what's inside with respect to t, which is minus a. Okay, if I take the next partial derivative, and I'll switch to the easier notation using subscripts, so u sub tt is the second partial of u with respect to t. I just use the chain rule again. I'll get f prime prime at x minus at. I've already had one minus a, and I'll get another minus a. So that's a squared f double prime at x minus at. Now let's try the x partials. So u sub x is, well, I take the derivative of f with respect to z, that's f prime at z, and I take the derivative of the stuff inside with respect to x, which is just 1, and similarly the second x partial will be f double prime at x minus at times 1 squared, which is 1. And so notice when I compare the left side of my partial differential equation to the right side, which is a squared u sub xx, they agree. They both equal a squared times f double prime at x minus at. So u sub tt equals a squared u sub xx. Those composition functions are solutions. And I could have done the same thing if I had taken u of xt to be f at x plus at. You can see, if you look up higher, that when I took the partial with respect to t, I'd get f prime at the x plus at times a plus a. When I took the second t partial, I'd get plus a times plus a, multiplying the f double prime. And that would again equal a squared times u sub xx. Okay, now what's the meaning of these solutions? Well, I pre-drew a picture here so I wouldn't have to waste time in the video. But this would work for any twice differentiable function f. Let's take what we call a bump function. Where the graph of f is 0 most places, but has a bump somewhere, and let's make the bump at 0. So this purple picture is the graph of f of x, which is also the graph of u of x 0. Okay, now let's compare that to the graph of u of xt, which is the graph of x minus at. Well, we know that when we replace x with x minus h, we move graphs over by a distance h. So this second graph is just the original graph translated by at to the right. And as t varies, that little bump is just moving to the right at speed a. So geometrically, what's happening here is that these particular solutions to the wave equation, they have a fixed profile, and they're just moving to the right with speed a. There are these little waves with speed a. And if I looked at the solutions f at x plus at, those guys would be moving to the left with speed a. So although we haven't explained where the wave equation comes from, we've already seen why it's a reasonable equation, because we get these solutions that we think of as traveling waves, and they're actually solutions to the partial differential equation. Okay, and you'll explore these ideas more in your homework, and we'll also come back to them in the next lecture. All right, so let's take a few minutes to look at what Wikipedia has to say about the wave equation. You'll see that it touches on a lot of the key themes in this course. Okay, so the wave equation is a second-order linear partial differential equation. It tries to describe wave motion, and applications include physics, vibrating strings, sound waves, water waves, seismic waves, light waves. So vastly applicable. Apparently, D'Alembert was the first person to think about vibrating strings, and other famous physicists / mathematicians in the 1700s were also studying this partial differential equation. Okay, more details. In the introduction here, they remark that in full generality, instead of just one space variable, you can have n space variables, and often it's just 3 because you're living in R3. This is the Rn wave equation. The R1 wave equation, which we just talked about on the first page, is u sub tt is, I called it a squared, but it's also often called c squared, where c is the speed because of the application to light waves. So in one space variable, it's the wave equation from the first page. Okay, and now here's some more themes from our course. The solution to this equation can be quite complicated, but they're always made out of linear combinations of simple solutions, because this is a homogeneous linear partial differential equation. Combinations of solutions are still solutions. Okay, that's a key theme. And I've also been using the word superposition either for homogeneous or non-homogeneous problems. So it's getting near the end of the course. It's good to think about what the key ideas have been, and linearity is definitely one of the key ideas in this course, and also in 2270, which was a prerequisite. Okay. To get unique solutions to the wave equation, you have further conditions. You have initial conditions, which tell you what the profile of the wave was at t equals 0, and they'll also tell you how fast that profile was moving. And very often, you're dealing with a wave on an interval from 0 to L, and so there will be boundary conditions as well. And so just as for the heat equation, the natural framework for unique solutions is initial boundary value problems. Okay, so let's talk about where the wave equation comes from. And in one space dimension. So consider, if you look at the picture lower on the screen, consider a function u of xt, which is measuring vertical or transverse displacement of a string, say, as it's vibrating, where at equilibrium, the string is just lying along the x-axis, and it has length L. Okay, so we're doing transverse displacements. And this is actually a complete analogy, sort of continuous limit of mass spring systems in this class. And this is the wave equation, which we're going to understand in a few minutes by modeling the vibrating string. Okay, so we already talked about the fact that it's a homogeneous linear partial differential equation. You could totally study the forced wave equation, which is non-homogeneous, but we don't have time to do that in this class. Okay, so here is the setup. Let me do a little bit of preliminary work here. So what makes transverse waves different than longitudinal waves, if you're looking at a string or a spring, is that the tension doesn't change under transverse oscillation when you linearize. So let's think about why that's true. So if you look at a small piece of the graph and do the tangent approximation, so this is the piece of the graph between x and x plus dx. The element of arc length, which is an approximation for the length of the curve over that short interval, is the square root of 1 plus dy dx squared dx. And if the y's are small, the square root of 1 plus y sub x squared is approximately, using the Taylor expansion for square root of 1 plus z, is approximately 1 plus 1/2 y sub x squared. And that's approximately 1 if, and the reason for that is it differs by a quadratic term. So if y sub x is small, say less than epsilon, then y sub x squared is less than epsilon squared. So to first order, when you do small transverse displacements of a straight line string or spring, you're not stretching it at all. Okay, and then the other thing I labeled in this picture is the tangent vector to the graph at the point x, y of xt. Yeah, so we're calling y of xt the vertical displacements. And the tangent vector is parallel to 1 y sub x, just using the tangent approximation. Okay, so let's derive the wave equation. So we're still looking at a little piece of the string lying above the interval from x to x plus delta x. This is a small oscillation, so the tension is essentially the tension that this spring would, or string would have at rest, which we're calling T naught. The tension gives you a force which acts in the direction of the string. So on the right endpoint, there is a force vector for the tension, which has strength T naught in the positive direction. Then that vector is just the tangent vector from the last page. To be technically correct, it should be a unit vector. So we would divide by 1 over the square root of 1 plus y sub x squared at that point. But as we were assuming that y and y sub x were small, then we can just neglect the quadratic term y sub x squared. And it's the same on the left, except the tension is pulling in the negative direction with magnitude T naught. Okay, and we're assuming this string is oscillating transversely. So, and if you look at it, the horizontal forces balance out, so that's consistent with no sideways motion, at least to linearization accuracy. So here is Newton's law. There's essentially no stretching going on, so rho naught is the density, mass per length, which is not changing to first order as the string vibrates. And so this is just mass per length times length for that little delta x segment, times acceleration, should be the net forces, and we're talking about the horizontal forces. And so if you look at the force diagram up above and look at the first entries, the second entries, which is the vertical, this is the vertical acceleration. On the right, we get a plus T naught y sub x at the right end point, and on the left, we get minus T naught y sub x on the left end point. And so this is just force equals mass times acceleration. Okay, if you divide by the delta x's, you get this equation. And as you let the delta x's go to 0, you see that you've just got difference quotients for the x derivative of y sub x, and in the limit you get y sub xx. And this is the wave equation. The coefficient here is positive, and I told you at the beginning we're going to call that a squared, and I explained why, because it's the speed of, a is the speed of traveling waves. Okay, so in this example, the speed depends on the tension T naught, and if T naught is bigger, that implies A is bigger. That makes sense. If you pull a string tighter and make it vibrate, you can hear the pitch go up. And if you have a slinky and pull it tighter and make a wave travel along it, the wave will go faster. And if rho naught is bigger, you're giving it more inertia, and so the speed A is smaller. Okay. So you can also model parallel or longitudinal vibrations. So I drew a diagram, looks like our old mass spring diagrams here. So if you're at x, then u of xt will be how much that point has moved at time t, displaced from equilibrium, and u at x plus delta xt will be how much that point has moved that was originally at x plus delta x. And because you're stretching, because the movement is different in different places, in this example you're stretching and compressing the string, and so the tension is not constant. And you can do a similar derivation as we did on the previous page, and you will again get a wave equation, but the speed will not be the same as it was for the transverse oscillations. It will turn out to be how the tension, how fast, the opposite of how fast the tension is changing as a function of rho at the initial density. And so T of rho is actually a decreasing function because having bigger rho corresponds to a less stretched string or spring, and therefore the tension is less. And so T prime of rho is negative, and negative T prime of rho is positive. Okay. If you dare, you could try to do the derivation for this. It's possible, it's just messier. It's worth mentioning these longitudinal vibrations because they come up in lots of applications. So sound waves are compression waves. And in particular, if you're playing a musical instrument, a wind instrument, you're making compression waves. Earthquakes, they generate both compression waves and transverse waves. The compression waves are called P waves for pressure, and the transverse waves are called S waves because that's what the ground looks like if you're looking at it and an S wave is passing you by. It's kind of interesting. I looked at Wikipedia to see how they derived the equation for pressure waves, and they do it as a limit of our favorite configuration, which is a series, one of them, a series of coupled mass springs. And if you take the time to look at this, which I'm not really going to do here, this should look familiar. So this is the net force at location x plus h, and they're just adding up the stretch displacements to the right and the left with the proper signs. It looks exactly like what we were doing in chapter, I forget. Anyway, they kind of take a limit of those mass spring configurations as the masses go to infinity and the forces are scaled appropriately, and at the end they get the pressure wave partial differential equation. Okay, and these are the compression waves. Longitudinal, parallel, whatever synonym you want. Okay. Now, I thought when I was thinking about the lecture that it might be nice to talk about these traveling wave solutions in the warm-up exercise instead of here. So we already showed in the warm-up that the special solutions f of x minus at and f of x plus at solve the wave equation. And we already interpreted these as traveling waves moving to the right or the left with speed a. And we already talked about the fact that it makes sense that if you increase the tension, the speed goes up, and if you increase the density, the speed goes down. Now, in analogy with what we did for the heat equation, let's talk about the natural initial boundary value problems for a vibration that is occurring on an interval of finite length L. So you want the wave equation to hold for all positive time and for all x between 0 and L. That's the shaded region in the diagram. Because this is a second order partial differential equation in T, and it makes sense physically too, you get to specify the initial displacement, u of x0. So think of the transverse oscillations. That's the initial profile of u at time t equals 0. And you get to specify the initial velocity, say in the transverse direction if you're doing the vibrating string. And then once you specify those two things, you still get to specify what's happening on the endpoints. And there are type 1 and type 2 boundary conditions that we impose. Type 1 is fixed endpoints, where u of 0t and u of lt always have to be 0. So picture a vibrating string or in a musical instrument also where the endpoints are fixed. And then there's the type 2 boundary condition, which is free endpoints. Remember, the vertical force is proportional to the x partial derivative, so saying free endpoints means you're not applying any force at the ends to keep them fixed, and that's u sub x is 0 at x equals 0 and L. And if you're thinking musically, string instruments have type 1 boundary conditions, and wind instruments have type 2. And string instruments, like I said, are transverse oscillations, and wind instruments are pressure waves. Okay, so altogether you can get you can get 4 kinds of problems. So the boundary conditions can either be type 1 or type 2. And then because you get an initial displacement and an initial velocity, you can break your initial boundary value problem down into 2 separate smaller problems. In the first one, you can specify just the initial displacement and set the initial velocity equal to 0. And in the second one, you can specify the initial velocity and then set the initial displacement equal to 0. And then if you add the solution to the first one to the solution to the second one, you get the solution to the most general one, where you're specifying both the initial non-zero initial displacement and initial velocity. And you can do this in the context of either type 1 or type 2 boundary values. So in that sense, this is harder than the heat equation, where we just had 2 types to consider, but the principles are exactly the same as in the heat equation. We're going to try to make building block solutions to solve, and then use superposition to solve the general type 1 and type 2 problems. Okay, so yeah, I call example 2 a nutshell, although there's enough letters going on that may not seem that concise. Actually, at the end of the lecture, we'll do a concrete example, which is the real nutshell. So let's go through the same considerations as we did for the heat equation. Let's think about the type 1 product solutions as well as the type 2 product solutions. And to save time, I wrote down the argument, but let's talk through it quickly. So just as for the heat equation, we're going to consider product solutions. U of xt is a function of x times a function of t. In type 1, where we want u to be 0 when x is 0 in L, we need the capital X to satisfy capital X of 0 and capital X of L are 0. And then we want to see when we can get solutions to the wave equation. So we need to compute u sub tt, which is the left side of the PDE. That will just be capital X of x times v double prime of t. We need to compute a squared u sub xx, which is the right side of the wave equation, and that'll just be a squared times capital X double prime at x times v. And those two things have to be equal to solve the wave equation. And then we separate the functions so that we've got the functions of x on the right and the functions of t on the left. And then both sides actually have to be constant, because if you freeze one of the variables, you can let the other variable change freely on the other side without changing the value on the other side. And therefore, capital X double prime over capital X has to be constant. If we call it lambda, we did exactly this in the heat equation, then we get the second order differential equation that we know from chapter 3. If we require capital X of 0 and capital X of L to be 0, then the the minus lambdas have to turn out to be positive numbers with trig function solutions. So we get sine of n pi over Lx, and this was xn double prime over xn, turns out to be, the lambda is minus n pi over L squared. So this is exactly the analysis that we did for the heat equation. Okay, so this is for type 1. If we were doing type 2, then because of the partial of capital X with respect to x needing to be 0 at both of the endpoints, you would get the cosine of n pi over L x's instead of the sine of n pi over L x's, and you would have the same eigenvalues. Xn double prime over xn would again be minus n pi over L squared. Okay, remember how for the heat equation, once we had the function of x, we went back to the starting equation where we were saying the product had to solve the PDE, and then we got a differential equation for the v of t. So we do the same thing for the wave equation. So we're looking at product solutions. We already know that depending on whether it's type 1 or type 2, the xn's are going to be sine n pi over Lx or cosine of n pi over Lx, and the xn double prime over xn will just be minus n pi over L quantity squared. So let's feed that into the condition, right, that was necessary to solve the wave equation. And that says that v double prime of t over v of t is a squared times, and these are indexed by n also, a squared times the x double prime over x, which was negative n pi over L squared. So multiplying by Vn and rewriting, this is Vn double prime of t plus a squared n pi over L squared Vn of t is 0. This is again a chapter 3 undamped, unforced oscillator. The solutions are linear combinations of cos and sine. The omega naught here is a times n pi over L. So we'll get those cosines and the corresponding sines with the same angular frequencies. And then finally, the u of xt's will be the xn's times the VNs. For type 1, the xn's were sine of n pi over Lx. Then we multiply by the VNs. So we can either get a cosine of A times the old angular frequency in the x direction times t, or we can get sine n pi L over x's times sines of A n pi over LT. So those building blocks will all be 0 when x is 0 or L, and they will all solve the wave equation. For type 2, we will get building blocks cosine n pi over Lx, cosine of A n pi over LT, and cosine n pi over Lx, times sine of A n pi over LT. And it turns out these are naturally paired off if you want to specify either initial displacement with 0 initial velocity or initial velocity with 0 initial displacement. So these two are to specify initial displacement because at t equals 0, the cosine of the A n pi over LTs evaluate to 1. So these specify initial displacement with 0 initial velocity, because when you take the t derivatives, the cosines turn into sines, and at t equals 0, the sines are 0. Whereas the bottom two are how you would specify initial velocity of the string without mucking around the displacement, because at t equals 0, the sine of t terms evaluate to 0 with 0 initial displacement. And then, if you want to be even more fancy, if you want the initial velocity to just be the sine n pi over Lx term or the cosine n pi over Lx term, you could divide these sine terms by A n pi over L, and then that would exactly cancel the factor you got when you took the t derivative of the sine terms and used the chain rule. Okay, so this looked long. One thing that I always like to remember is that the product solutions are products of sinusoidal functions. All possible four products depending on what you're studying. And here's the key thing. The time angular velocity that's the A n pi over L equals A times the spatial, the x angular velocity. Right? We're just saying that the t functions have angular velocity A n pi over L, whereas the x functions have angular velocity n pi over L. And this actually makes unit sense because the time angular velocities should be radians per second. A is a speed, so that's distance per second, or yeah, that's radians per time for the time angular velocity. A is distance per time, because it's a velocity. And spatial angular velocity is radians per distance, dx. So the units check out. All right, so that's a lot of letters. Let's do this summary example, and then let's go to Desmos, and I'll talk about the movie that we get, and about fundamental modes, and other stuff. So our favorite interval in these problems is x goes from 0 to pi, because then for type 1 or type 2, we're doing even or odd extensions. We're really talking about the interval from minus pi to pi, and our spatial sinusoidal functions are just sine nx or cosine nx, right? So in general, they're n pi over L, which will be n. So that's the spatial angular velocity. And then A times n will be the time angular velocity. Okay, and I did a combined initial boundary value problem. It is type 1 with fixed endpoints. So our spatial functions will be sines and not cosines, but you could do the analogous problem for a type 2. Our speed is 2 because a squared is 4. Okay, and we are specifying an initial displacement and an initial velocity, but luckily for us, they are both already in Fourier series form for the x variable. So we don't have to do something silly like recompute a Fourier series because it was given to us. So let's just write down what our solution is. So let me rewrite the initial displacement. And the initial velocity. And now let me write down u of xt. Okay, so 2 sine x. So that's an initial displacement. I need a t function which will be 1 at t equals 0. And have 0 initial velocity. My a is 2. My time angular frequencies are twice my spatial angular frequencies. So here goes a cosine of 2t. That product solution, when I take the second t partial, I will get 4 times the second x partial. It solves the PDE. It solves the first part of the initial displacement. It has no initial velocity. Next piece. Once you get the hang of it, this is super easy. Okay, the next displacement was a sine of 2x. For the time angular velocity, I have to multiply that 2 by 2, so I get a cosine of 4t. Okay, and then finally, I want to, so far what I've done has no initial velocity because at t equals 0, the sine of 2t and sine of 4t terms are 0. Here's how we do the initial velocity solution. There's what we were given. So I have to multiply it by some multiple of sine of 6t, because a is 2. And I should choose that multiple so that when I take the t derivative of the product, I get back the blue stuff, the 3 sine of 3x, and so the multiple is 1/6. Because the t derivative of 1/6 sine 6t is cosine 6t, and at t equals 0, that equals 1. That is a solution made out of building blocks. A lot of your homework is just like that. Please don't recompute the Fourier series if you've already got the right Fourier series, and it's a finite sum right there. Okay, so in a sec we'll go to Desmos, and we'll look at the pieces that this u of xt is comprised of. This first piece is called the fundamental mode for this fixed endpoint problem. It's the red curve at the right, so it's just a multiple of sine x of amplitude 2 actually oscillating, so the amplitude is really at any time t is really 2 cos t. So you're getting multiples of 2 sine x, which are going from +1 of it down to -1 of it and back. The next one is the second fundamental mode. That's the green one. It is oscillating twice as fast with an angular velocity of 4 radians per second instead of 2. If this was a stringed instrument, the sound of the second mode would be 1 octave up from the fundamental mode. The next one is the third fundamental mode. Might have something to do with fifths in music. Fundamental mode. And you don't see that, or you barely see that in the picture, because the picture is at t equals 0. And at t equals 0, that purple curve is lying right along the x-axis. And then finally, the black curve is the superposition of all the other homogeneous solutions so that we solve the initial boundary value problem. Okay, so let's go to Desmos and see this. Okay, so I have all three pieces typed in, as well as the superposition of all three. The first one, the red one, was the first fundamental mode. Remember, our interval is from 0 to pi. And, for a real wave, this is supposed to be small oscillations, so the vertical axis would actually be scaled down by a factor of 100 or something, but you can visualize it this way. Okay. Let's watch the second fundamental mode. I'll actually do it with the first one, and you'll see that the second one is oscillating twice as fast as the first one. And now I'll add the third fundamental mode, which is oscillating 3 times as fast as the first one. And finally, the superposition of all three. I could leave, let's just look at the single superposition, which was the initial boundary value problem. So that looks pretty wild. But its component pieces are just the fundamental modes. So as the Wikipedia page was talking about, and we've seen this in how mass spring systems oscillate before, by using these building block solutions, we are breaking a complicated problem down into a bunch of neat vibrations, just like the carbon dioxide homework problem, I guess. And that's the way to understand the wave equation, as well as lots of other phenomena. Okay, so this is a great place to stop, and so let's stop.